Hello everyone, and welcome to the Chapter 7 lecture. Chapter 7 is all about chemical reactions. And so we're going to talk about how we write chemical reactions, and we're going to talk about classifying different types of chemical reactions, and in particular we're going to talk about a specific type of reaction called precipitation reactions. And then we're going to spend a lot of time doing something called stoichiometry, which is basically recipe adjustments in chemistry. So we're going to do that in a second part of the lecture. So this one's the first part of the lecture. We're going to talk about how to write chemical equations and classify them, and a lot about precipitation reactions. All right, so chemical reactions, we can write them out as equations, kind of like a math equation. And in a chemical equation, everything on the left side of the reaction arrow are the reactants. And the reactants are our starting materials. All right, and everything on the right side of the reaction arrow are the products. And the products are the new chemicals that are formed. All right, so this reaction as written is not balanced. It needs to be balanced. And what do we mean by that? So chemical equations need to have the same number of elements of each atom, or the same number of atoms of each element on both sides of the equation, due to something called the law of conservation of matter, which says that we can't create or destroy matter, we can only rearrange it. All right, so matter can't be created or destroyed, it can only be rearranged. So for example, if we look at these hydrogens, there's 4 hydrogens on the reactant side and 2 hydrogens on the product side. All right, that can't be. What happened to those the other two hydrogens? They can't just poof, disappear, all right? Because of the conservation of matter, we can't disappear things. So we need to balance this equation, and we can balance it using numbers that we call coefficients. And a coefficient is a number in front of the formula in the reaction. So for example, if I wrote 2CO2, all right, this 2 in front, that is a coefficient. All right, that's what we're referring to as a coefficient. Unlike this little 2 here, which is a subscript. All right, we don't manipulate subscripts when we're balancing an equation, because that's telling us that this is carbon dioxide. It's a molecule that has 1 carbon and 2 oxygens, all right? And this number tells us that we have 2 of those molecules. We have 2 carbon dioxide molecules. So balancing equations is really a trial and error process, which can sometimes frustrate students who are looking for, specific steps to follow to solve a problem. So if we were to break it down into steps, I suppose we could say balancing is 2 steps. The first step is to count the number of atoms of each element on both sides. And a good way to do this, to sort of visualize it, is to create a table. Right? And you're welcome to do this for problems as sort of a beginner's way to balance before you learn to kind of just do it in your head. So carbon, on the reactant side, we have 1 carbon, we have 4 hydrogens, and we have 2 oxygens. That's what those subscripts mean. On the product side, we have 1 carbon, we have 2 hydrogens, and we have 2 plus 1 for 3 oxygens. All right, so now we have tallied up, we've counted the elements on both sides. Now the second step is to add coefficients to balance it, and we can do this one at a time. So I'm looking at carbon. I'm not going to do that one first because it's balanced. If I go down the table, the next one is hydrogen, and we can balance hydrogen next. Another reason to save oxygen for the end, besides the fact that it's the last one I listed, is that it's best to leave single element substances for last. And since oxygen is a single element substance in this problem, we're going to save oxygen for last for balancing here. All right, So let's switch up my colors here. We'll use blue. So hydrogen, we've got 2 hydrogens over here on the product side, and I want to have 4. So if I put a 2 coefficient in front, 2 times 2 is 4. So now my hydrogens are balanced. I've also changed the number of oxygens by adding that coefficient of 2. 2 oxygens, so 2 times 2, blah. So I've got 2 oxygens here, and I have 2 oxygens here, so that's a total of 4 oxygens. All right, so I've got my 2 coefficient, and now I need to balance oxygen because I only have 2 on the reactant side. So I need to put a 2 here, and that will change it to 4 oxygens on the reactant side. So now I have 1 carbon, 4 hydrogens, and 4 oxygens on both sides of the equation. Now it is balanced. I have conservation of matter. No elements were created or destroyed. All right. So one other example I have here, we've got potassium plus fluorine reacts to form potassium fluoride. All right, so if we balance this one, remember we put coefficients in front of the substances. All right, so I have 1 potassium, cool. I have 2 fluorines and only 1 fluorine. So I can put a 2 here. So now I have 2 fluorines on both sides, but I've multiplied my potassium. So if I put a 2 here, now I am balanced. In other words, this blank spot here really indicates a coefficient of 1, but we don't usually write that. So 1 is understood. If nothing's there, then we know we consider that coefficient to be 1. All right, so notice how we said 2 KF, all right? When we were trying to balance that fluorine, what we did not do is we didn't try to stick that 2 in the middle, okay? You can't stick a coefficient in the middle of a formula, only in front of the formula, okay? So don't try that. Don't do it that way. That's not a thing. That's just messed up, all right? The other thing is you never want to try to add subscripts, okay? So we never want to try to balance it by doing this, by taking that KF and then putting a 2 here, all right? Those two things are not the same. So we cannot put a 2 subscript on the fluorine in order to balance this equation, okay? Because then we're changing the product. We're changing it to a totally different compound. In fact, KF2 is a totally fictional compound. It can't exist because it's an ionic compound made up of potassium and fluoride, all right? 1 plus charge and a 1 minus charge can only combine in one way to form KF. All right, so KF2 is a totally fictional element. So if you put a subscript there, not only are you changing the compound, but you also may be changing it into something that doesn't exist. All right, so just remember, coefficients always go in front of the substance. That's a key thing to remember. All right, so let's practice. Let's do some practice ones. I'm not going to draw out a table here, but I will kind of indicate as I go our counts. All right, so let's look at sodium. Sodium and sodium. That's good. All right, we don't need to do anything there. Chlorine and chlorine. So we've got 1 chlorine and 2 chlorine. So I need to fix that by adding a 2 here. So now I have 2 chlorines on both sides of the equations. But now I've also made 2 sodiums on the reactant side. So I'm going to add a 2 here to balance my sodiums. So I've got 2 sodium, 2 sodium, 2 chlorine, 2 chlorine, 1 copper, 1 copper. Everything checks out. We are now balanced. So check. All right, now the next one. We've got cobalt oxide plus carbon reacts to form cobalt plus carbon dioxide. So let's see, we've got 2 cobalts here and 1 here. So I'll balance that by sticking a 2 there. And then I've got 3 oxygens and 2 oxygens. Be careful here because cobalt C little o, all right, and carbon dioxide is a big C big O. Remember, capitalization is important in chemistry, so this is not oxygen, this is part of cobalt. This is the oxygen. So we have 2 oxygens and 3 oxygens. Let's do that to make it an oxygen, okay? There's nothing I can multiply this product side by to give a whole number. And we want to have whole number coefficients. It's just cleaner that way. So what I'm going to need to do is multiply these to get a least common multiple. So if I multiply this by 3 and this by 2, then I'll end up with 6 oxygens on both sides. So that's what I'm going to do. So if I multiply those by 3, now I have 6 oxygens on both sides. My oxygens are balanced, but check this out. I messed up my cobalt. So now I have 2 times 2 cobalts. So I need to erase this 2 and change that coefficient to a 4. All right, this is why this is a trial and error process. I tried that 2 and it was an error, so I had to erase it and change it to a 4. So now my cobalts are balanced. And then lastly, the carbon. If I add a 3 there, then I have 3 carbons on both sides. So now everything has the same, the cobalts, the oxygens, and the carbons are balanced on both sides of the equation. And this last one here, C4H10, so I'll start with carbon. I've got 4 over here, only 1 over here, so if I put a 4 in front, now my carbons are balanced. Next, let's do hydrogen. I've got 10 on the reactant side and 2 on the product side, so if I put a 5 here, 5 times 2 is 10. So now I have 4 carbons and 10 hydrogens on both sides. And now I just need to balance my oxygens. So let's see, over here I have 4 times 2 in the carbon dioxide. So I have 8 oxygens in the carbon dioxide. And 5 times 1, 5 oxygens in the water molecules. 8 plus 5 is 13. So I have a total of 13 oxygens. That's kind of a problem because that's an odd number. And over here I have O2. So I can't multiply this by a whole number to get 13. I'd have to multiply it by 6.5 to get 13. So since I want to have all whole number coefficients, what I'm going to do is multiply this whole equation by 2. If I multiply all of these coefficients by 2, then I'm going to get this equation. 2C4H10 plus 13 O2 reacts to form 8 CO2 and 10 H2O. So this would be our balanced equation. We want those coefficients to be whole numbers, and we want them to be the lowest whole numbers possible. So we want them to be simplified. So for example, for this first equation up here, all right, an example of what we don't want is this. Oops. Nope, I just messed that up. Hold on. Try that again. Okay, perhaps you did balancing and you did your trial and error back and forth, and you end up with this. All right, this would not be correct because this is not the simplified version. All right, so it's kind of like empirical formulas. So we want it to be simplified. So what we could do is divide this whole thing by 2, divide all of those coefficients by 2 to get simpler coefficients, all right, and get the right equation. All right, so balancing equations is one thing when you're given the equation and you're given the formulas, and then you just have to do your back and forth balancing, all right? something that students really struggle with, though, is writing balanced equations from a sentence. So in this case, before you balance it, you first have to write it out. And the first step is to write out the correct formulas for all the reactants and products. You learned in Chapter 4 how to name ionic and covalent compounds. So if you're given the name of the compound, you should be able to write the correct formula for it. Another one to note that we haven't explicitly talked about yet are the diatomic elements. And these you should memorize, and there's a nice handy-dandy mnemonic for it, and it is Hofbrinkel. Hofbrinkel. All right, which is to say that hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine are all diatomic, meaning that when you have pure hydrogen gas or oxygen gas, right, it's actually molecular oxygen. It's two oxygens that are bonded together, and same thing with hydrogen and all these different 7 diatomic elements, all right, in their natural state. So if you have a problem where it says you react methane and oxygen, you need to know that oxygen is actually O2, not O. All right, so that's something that can trip students up, is those diatomic elements. So let's do some examples. All right, this first one, we have molecular nitrogen and molecular hydrogen react to form ammonia. So first thing we need to do is write out actually I just want to do this in a different color. I like keeping red as my coefficient color. All right, so we've got molecular nitrogen, N2, it's one of the diatomic elements. Hydrogen, also one of the diatomic elements. React to form, so that's our reaction arrow. And our product is ammonia. All right, so now we've written out the equation. We have all of the compounds and elements written correctly. Now we need to balance it. And to balance it, we need to add coefficients. So we're going to add a coefficient in front. Oh, my cat is on me. This is going to be tricky. Okay, so nitrogen is not balanced. We need to balance nitrogen. We're going to put a 3 right here in red. And nope, not a 3. Just kidding. We have 2 nitrogens. Trying to see through my cat. I don't know if you can hear her purring. All right, so now we've got 2 nitrogens on both sides of the equation. And 2 times 3 is 6 hydrogens. So I need a 3 over here to balance my hydrogens. Yay, now we have a balanced equation. The next one, we've got aluminum reacts with oxygen gas to form aluminum oxide. Aluminum is not a diatomic element, so aluminum is just aluminum. Oxygen, though, is diatomic, so oxygen is going to be O2. Can you hear my cat purring? She loves doing chemistry, guys. All right, and then we've got aluminum oxide. Aluminum oxide is an ionic compound. Remember, ionic compounds don't tell you in the name how many atoms of each. So it could be ALO, but it isn't necessarily. We need to know the charges on these different ions. Aluminum is a group 3 element. It has a 3+ charge. And oxide is an oxygen ion that has a 2- charge. We get these just by looking at the periodic table. So they're not going to combine in a 1-to-1 ratio. In order to balance out the charges and have a neutral compound, we need to have 2 aluminums and 3 oxygens. So the correct formula for aluminum oxide is Al2O3. Now that we have the correct components written out, the correct compound formulas written out, now we can balance it. So I need a 2 here for my aluminum. And, we gotta do some funky math. All right, so 2 oxygens and 3 oxygens, we're going to do this so that I can have whole numbers. So we've got, a 3 here. All right, so now I've got 6 oxygens on both sides of the equation, and I have 4 aluminums on the product side, so I need a 4 in front of my aluminum. All right, so notice how I'd started with a 2 in front of the aluminum, and then I realized that was wrong and I needed to change it. That's the whole trial and error element of balancing equations. All right, and then for this last one here, we've got nickel 2 nitrate. All right, nickel 2 means it has a 2 plus charge. Nitrate 8 tells us that's a polyatomic ion, and we look it up, it's NO3 and it has a 1 minus charge. All right, so nickel nitrate, the formula for nickel nitrate looks like this. Okay, so, and it reacts with sodium carbonate. That is a polyatomic ion carbonate. We look it up, CO3 with a 2 minus charge. Sodium is on the periodic table. It has a 1 plus charge. So the formula for sodium carbonate is going to be Na2CO3. I don't need parentheses. All right, I need 2 sodiums and 1 carbonate. They're going to react to form nickel 2 carbonate. Well, nickel has a 2 plus charge and carbonate has a 2 minus charge. So it's just nickel carbonate. And sodium nitrate. Sodium has a 1 plus charge, nitrate has a 1 minus charge. So that's the formula for sodium nitrate. Now we got to balance it. Nickel is balanced, I'm good there. Sodium, I've got 2 on the reactant side, I need 2 on the product side, so I throw a 2 there. Now I also have 2 nitrates, all right? When you're balancing equations with polyatomic ions, I'll just write this out for visual, all right? We keep the polyatomic ions together. So we don't have to separate them into nitrogen and oxygen and carbon and oxygen, right? We can just keep them together, and I'll show you. We've got 1 nickel on each side. We've got 2 nitrates over here and 1 nitrate over here before I added that coefficient. And originally we had 2 sodiums over here and 1 sodium over here, 1 carbonate and 1 carbonate. So I added that 2 coefficient, and now I have 2 nitrates and 2 sodiums. So now we got a balanced equation. All right, so practice, practice, practice balancing equations and writing balanced equations. Other things you might see in an equation that we left out of those that I just wrote up there are the physical states of elements. So you might see a little S for solid, or an L, usually a cursive L for liquid, or a G for gas. Or a fourth thing that you might see noted is AQ for aqueous. Aqueous means that something is dissolved in water. So for example, this equation here, we would read that as 4 molecules of iron, solid iron, react with 3 molecules of gaseous oxygen to form 2 molecules of solid iron oxide, or rust. In fact, this is the reaction you performed in your hydrogen peroxide and steel wool lab. Another thing that you might see in a chemical reaction, wow, I really spelled that wrong there. You can change that. Are initiators. So initiators are things that are needed to start a reaction. A lot of times reactions need heat to get going, or they might need energy from light, or they may need a catalyst that helps the reaction proceed faster. And so since those things are not directly involved or changed in the reaction, we don't put them on the reactant or product side, we simply put them over the reactant arrow. So like if a reaction needs heat, you'll see that little Greek letter delta over the reaction arrow, or if it is catalyzed by an enzyme, you might see the name of the enzyme over it. So like if this was a different reaction, it might be, you might see lactase or hexokinase, different names of enzymes can be pictured above there. Okay, So that's another thing that you might see in a chemical reaction. All right, so we can classify chemical reactions into some broad categories. There's 4 really main categories of types of reactions. The first is called a combination or synthesis reaction. Combination or synthesis reaction. RXN is a common abbreviation for reaction in chemistry. So in a combination or synthesis reaction, 2 or more chemicals are reacting to form one substance. So generically, we could write that as A plus B react to form C. And an example of this is actually that equation that we just saw up above. 2 hydrogens plus oxygen reacts to form water. So we have 2 substances reacting to form one substance. All right. The opposite of a combination reaction is a decomposition reaction. And in a decomposition reaction, you have one substance reacting to form 2 or more. So A decomposing into B and C. So an example of this type of reaction would be mercury oxide decomposing into 2 mercury atoms and 1 oxygen molecule. Then we have the replacement reactions. So the first kind, we call this either a substitution reaction, or a single replacement. Sometimes it's called a single displacement. So single replacement or single displacement reaction. And this is one that I like to affectionately refer to as a homewrecker reaction. So in a single displacement reaction, the sort of generic form of this would be A, B plus C reacts to form AC plus B. All right, so in this reaction, you have one element replacing another element in a compound. In this case, C replaces B in that compound. In my mind, C is the homewrecker. C is the single person that comes in and breaks up a happy couple and steals partner A and leaves B kicked out on the street. So an example of this reaction would be Cl2 plus 2CH3F reacts to form 2CH3Cl plus F2. In this case, the chlorine is the homewrecker that kicks out the fluorine and replaces it in the compound. All right, and then lastly, we have double displacement or double replacement reactions. And this is when you have 2 elements that swap compounds. So my analogy here is that I call these swinger reactions. All right, so swingers in a relationship sense are couples that switch partners. So if we had AB plus CD, and they switched partners, so then A and D got together, and C and B got together. That would be a double displacement. So in other words, what happened was A and D got together and B and C got together. That's how we did the swap here. So an example of a double displacement or double replacement reaction would be this. 2 NaCl plus Ag2SO4 reacts to form Na2SO4 and 2AgCl, silver chloride. All right, so in other words, the sodium and sulfate paired up, and the silver and chloride paired up. So they swapped partners. The cations and anions swapped partners. So a specific type of double displacement or double replacement reaction that we're going to talk about are precipitation reactions. And precipitation reactions happen in aqueous solutions. So an aqueous solution is any solution that uses water as a solvent. And water is a really excellent solvent because if we draw the Lewis structure of water, all right, looks like this. And remember, oxygen is one of those electron hogs. It's very electronegative. It hogs electrons and ends up with a partial negative charge. And hydrogen ends up with a partial positive charge. It's a polar molecule. It has these different charge poles or partial charges. And ionic compounds are made up of charged particles. So when you put an ionic compound in water, as long as it is soluble, then it will dissolve or dissociate into its ions. Okay, so for example, sodium chloride in water will dissolve into sodium ions that we say are aqueous, they're dissolved in water, and chloride ions that we say are aqueous or dissolved in water. So if we think of these sodium ions, these sodium cations, all right, as being positively charged particles, all right, they interact with the partially negative part, the partially negative oxygen of water molecules, and they'll be surrounded by the oxygens of water molecules. And the chlorines, all right, since they are negatively charged, the negative ions will interact with the partial positive charge on the hydrogens of the water molecules. So this diagram here is just showing you how you have, if you have a soluble salt in water, all right, the salt or the ionic compound is made up of positive and negative ions, and they will dissociate and spread apart in this water, and the water molecules will assemble themselves around those ions and evenly distribute them. All right, so how do you know if a salt, an ionic compound, is soluble or not? Well, there's a series of solubility rules that we follow. Okay, so the solubility rules are as follows. The first one is that any compound that contains an alkali metal, that is a group 1A element, all right, or an ammonium ion, okay, those are always soluble. There are no exceptions, okay, no exceptions. They're always soluble. The second rule is that if a molecule contains or a compound contains nitrate, a bicarbonate, or a chlorate, all right, it too is always soluble. No exceptions. Rule 3, if it contains a halide, so one of the group 7A elements or ions, all right, chlorine, bromine, iodine, fluoride, okay, then it is going to be soluble, except there are some exceptions, unless it has silver, mercury, or lead as its cation. All other chlorides, bromides, iodides, fluorides are soluble except for silver, mercury, and lead. And then sulfates are also almost always soluble, with the exception of silver, calcium, strontium, barium, mercury, and lead. Okay? And then rule 5 here, now we're talking about ones that are almost always insoluble. So carbonates, phosphates, chromates, and sulfides are nearly always insoluble. The exceptions are, of course, anything that has, if it has an alkali metal or an ammonium ion, because those are, rule 1, always soluble. All right, and then rule 6 here is hydroxides, having to do with hydroxides. Hydroxides are almost always insoluble. The exceptions are if there's an alkali metal ion, because that qualifies under rule 1, or a barium ion. Barium hydroxide is fairly soluble. Okay, so let's practice this. Let's look at some different salts here and determine whether they are soluble or insoluble using these solubility rules. So the first one, we have sodium iodide. Well, sodium is a group 1 element, and that's rule 1. Anything containing sodium is always going to be soluble. So I can look at the next one, sodium sulfide. Again, it has sodium. Sodium is going to make it soluble. No matter what comes after the sodium, it doesn't really matter, because if there's a group 1 element, it will always be soluble. Now let's look at these calcium salts. So we've got calcium chloride. Well, let's see, there's no rule about calcium, but there is a rule for chlorides. So that's rule 3 here. Chlorides are always soluble unless they have silver, mercury, or lead, and calcium is not one of those exceptions, so calcium chloride will be soluble. How about calcium carbonate? There's no rule for calcium, but there is a rule for carbonate. Rule 5 here says that carbonates are always insoluble unless they contain an alkali metal or ammonium. Calcium is not an alkali metal or ammonium, so it is insoluble. Calcium nitrate. Again, no rule for calcium, but there is a rule for nitrate. Nitrates are always soluble, no exceptions, so boom. And then lastly, calcium sulfate. Sulfate is right here. All right, sulfates are pretty much always soluble except for when there are one of these ions, and calcium is one of those ions. So normally sulfates are soluble, but calcium sulfate is an exception, and it is insoluble. Okay, so if a salt is insoluble, it stays solid. It doesn't dissolve in solution. Okay, so soluble, any type of soluble salt will be aqueous in solution, and an insoluble salt will be solid in solution. All right, so a cool, fun type of chemistry reaction that can be done are something called precipitation reactions. All right, so a precipitation reaction is a type of double displacement reaction, a swinger reaction, where we have two aqueous ionic compounds. And remember, an ionic compound is a salt. So sodium chloride is not the only salt. Any ionic compound is a salt, and I will use those terms interchangeably. All right, so we have two aqueous salts that can react to form an insoluble salt. So for example, here's a reaction here pictured. So in the beaker up here, we have potassium iodide, and in the beaker down here, we have lead to nitrate. All right, notice that these solutions are both clear. They look like water. But when we mix them together, in the second image here, you see this yellow precipitate forming, okay? Because the lead ions and the iodine ions form an insoluble salt, lead iodide. All right, that's what is forming this solid precipitate here, okay? So you'll notice that the nitrate and the potassium ions stay in solution, and that solution above it stays clear, but the lead iodide will precipitate out. So when we are writing precipitate reactions or solving precipitate reactions, if we have two aqueous solutions and we want to know, is it going to form a precipitate? There's a series of steps that we will follow. So the first one is start with the reactants and determine their ions. So we said that potassium iodide is in aqueous form is really just a solution of potassium ions and iodide ions. And lead nitrate, since it's in aqueous form, is really just a combination of lead ions and nitrate ions. Nitrate has a 1- charge, so that means that lead in this case, must have a 2+ charge. Lead is a transition ion, so we have to figure it out from this formula. We can't just look at the periodic table. Okay, so we know what ions are in this solution, these solutions, I should say. So then the second thing we want to do, we know this is a double displacement reaction, so we want to swap the partners. All right, so we want potassium to pair up with nitrogen and iodine to pair up with lead. All right, so if potassium and nitrate get together, that forms potassium nitrate. And if the lead and iodine get together, we always want the cation first, then we end up with lead iodide, PbI2. All right, so now we figured out what the products are. Those are the product formulas. But we also need to know which one of these products is forming the precipitate, which one forms and which one is insoluble. All right, so KNO3, we use the solubility rules. Potassium is a group 1 element and it's always soluble. Nitrates are also always soluble, so this one is definitely soluble and will be aqueous and dissolved in solution. Lead iodide. Iodides are usually soluble, but one of the exceptions is if it's bound to lead. So lead iodide from the solubility rules is insoluble. In other words, it will remain solid in the solution. So now we can write out the whole equation. So we had potassium iodide and lead nitrate. And we figured out that they're going to react to form potassium nitrate and lead iodide. That the lead iodide is our solid precipitate, and all of these others are aqueous in solution. So we've written out the full reaction. Now we can balance it. The last thing we want to do is balance. So let's see, my potassiums are equal on both sides. Lead is equal on both sides. Iodine is not. If I put a 2 here, now I have 2 iodines. And now I need to fix my potassiums. So I'm going to do 2 over there. So now I've got 2 potassiums, 2 iodines, 1 lead, and 2 nitrates on both sides. Check. We are balanced. So this would be the full balanced equation for the precipitation reaction that occurs between potassium iodide and lead nitrate. So this equation as written is what we call a molecular equation. The molecular equation. And that's one way to write out the equation for this precipitation reaction, where we've written out each of these salts as ionic compounds. All right. But as we know, that aqueous state means that they're actually dissociated in solution. So there's another way we can write it out. So let's work with a new equation here. So here's our new equation. Potassium carbonate aqueous plus calcium nitrate aqueous reacts to form potassium nitrate, and which is aqueous, and calcium carbonate, which is not. It is soluble. Or sorry, it's solid. And now I just need to balance this by throwing a 2 right there. So, okay, so this is our equation that we're working with. So this would be a molecular equation. We've written out the formulas for each of these salts as compounds. All right, and then we've just indicated which ones are aqueous. But of course, these aqueous salts are actually dissociated in solution. So the more correct way to write it, or sort of what reality really represents, the equation that represents reality best is called the complete ionic equation. All right, and in this, we take all of those soluble salts and we write them as dissociated ions, but we keep the insoluble salt, the precipitate, in its compound form. So we take that potassium carbonate and we say that it breaks up into 2 potassium ions and 1 carbonate ion, and we write the charges on each of those ions. The calcium nitrate breaks up into, or dissociates into, a calcium ion and 2 nitrate ions. And on the product side, that potassium nitrate breaks up or dissociates into 2 potassium ions and 1 nitrate ion. Or no, sorry, 2 nitrate ions, because there's 2 potassium nitrates. So we multiply both of those ions by 2. And then lastly, our calcium carbonate does not dissociate because it is not soluble. It is our precipitate. All right, so all of these ions should be written in the aqueous form, and they should include their charges as well. All right, and you'll notice that in a chemical equation like this, just like in a mathematical equation, sometimes you'll find that there are identical variables on both sides of the equation. So for example, we've got the potassium ions, all right, and our nitrate ions here, all right. When you have the same thing on both sides of the equation, you can cancel them out. All right, those ions that are showing up on both sides of the equation, they have a name. We call them spectator ions. A spectator is someone who just watches something, right? And so these ions are not actually involved in the precipitation. They're just watching it happen, but they're not involved in it. They're just floating around, staying in solution. So a simplified form of this ionic equation is called the net ionic equation. And this is where we just write the ions that are involved in the precipitation reaction, and we don't include those spectator ions. So in this case, we would just write the carbonate and the calcium ions reacting to form calcium carbonate, which is a solid. And here I will indicate that each of these are aqueous. I didn't do that in the complete ionic equation just because it takes up too much room. It takes up a lot of space, and I don't think I could fit those aqueous indicators in there. But certainly include them for the net ionic equations. All right, so let's practice some of these. We've got 2 different setups here. We want to write molecular, complete, and net ionic equations for each of these. So this first one, we have calcium chloride and silver nitrate, and they are aqueous. So the first thing I want to do is sort of write out what ions I actually have in these solutions. So both of these salts are soluble and are dissociated into their respective ions. Okay, so now I'm more ready to write the molecular equation here. So I've got calcium chloride in its aqueous form and silver nitrate in its aqueous form. And the products are going, this is a double displacement reaction, right? So the calcium and the nitrate are going to pair up. So we will have calcium nitrate, right? Calcium has a 2+ charge, nitrate has a 1- charge, so I need 2 of those. And the chlorine and the silver will pair up. I always want to write the cation first, so that's going to be silver chloride, right? I need to figure out which one of these is aqueous and which one is solid. In other words, which one is our precipitate. Calcium nitrate. Nitrates are always soluble, so this is going to be aqueous, dissolved in solution. Silver chloride. Chlorides are usually soluble, but silver chloride is one of the exceptions that is insoluble, so silver chloride is our precipitate, our solid. Okay, so I wrote out the products, I figured out which one was the precipitate, and the last thing is to balance the equation. So let's see, I need oops, nope. I need a 2 over here because I need 2 chlorines on both sides. And now I need 2 silvers, and now I have 2 nitrates. So now we are balanced. So next up is the complete ionic equation, where I'm going to take all these aqueous salts and dissociate them into their ions. So I have calcium ions plus 2 chloride ions plus 2 silver ions plus 2 nitrate ions. And we've got calcium ions, 2 nitrate ions. And our precipitate does not dissociate. It's the only one that stays as a compound. All right. And then we can do the net ionic equation, where we just write the ions that are involved in this reaction, where we cancel out those spectator ions. And if we do that, then we get 2 silver ions plus 2 chloride ions react to form 2 silver chloride. And now I will include the states of those ions being aqueous. All right, so just to point out to you, the spectator ions are the calcium and the nitrate ions. Okay. Next one. This one is similar, but instead of giving us the formulas, it names them. So it says aqueous magnesium chloride and aqueous potassium hydroxide. So magnesium chloride, magnesium has a 2+ charge, chloride has a 1- charge, so magnesium chloride is MgCl2, and it's aqueous. And then we also have potassium hydroxide. All right, the formula for that's just going to be KOH, aqueous. So for our molecular formula, we are starting with magnesium chloride, aqueous, and potassium hydroxide, aqueous, and we are doing a double displacement reaction. So the magnesium and the hydroxide will now pair together. So we get MgOH2 because hydroxide has a 1- charge, magnesium has a 2+ charge. And the chlorine and the potassium are going to pair together. That's potassium chloride. So now we need to determine which one is aqueous and which one is a solid. Potassium chloride, potassium is a group 1 element, and group 1 elements are always soluble, so that will always be aqueous. Magnesium hydroxide, hydroxides are generally not soluble in water. There's a couple of exceptions, but magnesium is not one of them. So it is insoluble. That's going to be our solid precipitate. So now for the complete ionic equation, magnesium ion plus 2 chloride ions plus a potassium ion plus a hydroxide ion, all of which are aqueous, react to form magnesium hydroxide, our solid precipitate, stays together, and potassium ions and chloride ions. Oh, I forgot to balance. Silly me. So I need to go to the molecular formula and make sure I'm balanced there. I've got, and so, okay, well, this is a good thing to point out. So I'm looking at my spectator ions, and I've got 2 chlorides over here and 1 chloride over here. And that's what kind of clued me into, like, wait a second, I'm not balanced. So I'm going back to that molecular formula. I need to do some balancing. If I put a 2 here, I've got 2 chlorides on both sides, and I put a 2 here, so I have 2 potassiums and 2 hydroxides on both sides. So now in my complete ionic equation, I just need to update my coefficients here. 2 and 2, so that they are balanced as well. All right, and then lastly, the net ionic equation is going to just be the magnesium and those hydroxide ions reacting to form magnesium hydroxide, that being our solid precipitate, each of these ions being aqueous in solution. And if it asked what are our spectator ions, what are they? Well, in this case, it would be our potassium and our chlorines. They are the spectator ions. They're the same on both sides of the equation. They cancel out. They are not doing anything. They are just staying aqueous, while the magnesium and hydroxide ions are pairing up and falling out of solution. So that's enough for the first part of this chapter to get you practicing in the homework, balancing equations, writing equations and then balancing them, and doing some practicing solubility rules and writing out precipitation reactions.